That should work better. Yeah, that's better. I just have no idea why it would do that. I've got to get my Microsoft Stream happening. Channel happening. There's about 8 million clicks required to get a stream happening sometimes. And everything is easy except for Microsoft Stream. So maybe in future we just won't do Microsoft Stream because it's dumb. It's not dumb. It's just too complicated. Not a very much loved product. Yeah, I want to connect my encoder. Yes. You have to move between like 3 screens just to get a streaming set up on Microsoft Stream. Whereas all the other streaming services just seem to automatically figure things out with an API. Isn't that funny? Let's move my laptop somewhere else. I'm gonna get a couple of PDFs open for you. 6821 datasheet. Something about something else. Okay, a few folks are watching. Thank you so much for joining me this morning, my team. I'm just going to get myself on Teams. Start my recording. Good morning, COMP2300. Thank you so much for joining me here on this Thursday morning, and it's gotten very cold here in Canberra, so you won't have wanted to get out of bed this morning to start your coding, or maybe you still haven't. In any case, I'm here to talk a little bit more about, I guess, our little tour of architecture through the lens of retro computing, which is maybe a bit of a weird place to start, but I think it's interesting to see a computer where you can really understand where all the bits are. Because modern computers, of course, are very, very complicated. Even your microbit is very, very complicated compared to the computer we were having a look at last week, and we'll continue to have a look today. After I do that today, I'm also going to do a few more demos on a microbit with a few features that I thought were interesting, or things to raise some discussion, hopefully, around the kind of the operating systems context switching area. So, I've got my coffee, so we're ready to go. I'm just going to briefly jump through the admin time for today. You know that there's an assignment due on Sunday. A little extension for that. I know that folks in this class are working very, very hard because it's week 11 and week 12 coming up. You have many assignments for many classes happening, big projects getting delivered. These are sometimes the toughest weeks of the semester, and the exam periods feels like more like a holiday compared to week 11 and week 12. So you've just got to tough it out. If it feels like it's a lot of pressure, that probably means that it's working, because it's supposed to be pressure. You're supposed to feel that these assessment items are important to you and that they're hard and that you want to do a good job. So yes, there's pressure. That's the way that things work when you're doing something that's hard and that you care about. So I hope that you've had a chance to attend the week 11 labs, and I hope that you've had a chance to try out some C programming on the microbit and have a go with that. In particular, I'm interested in whether you think that C programming on the microbit is now easier or harder than assembly. Because I feel like when your brain gets used to assembly, you get used to a certain kind of control over the computer, like, put this in this register right now, thank you. And then when you're in C and it doesn't let you do that, you feel like, oh, this programming language, this compiler doesn't know what I want. I know what I want. So maybe you've gotten very used to being the compiler for your own system, and it might take a minute to unlearn that expectation and get back to the normal situation, which we usually have when coding on computers, which is to have a quite advanced compiler or interpreter in between us and assembly instructions or machine instructions running on the chip. Sup Finn, thank you for joining me in the chat. At least I've got one Thursday morning fan. So, do remember that your current labs will be assessed through the lab pack. That's the last assessment piece, the last assignment, I guess, that's we're doing in this course. And it's also sort of the last opportunity you have to do some coding and submit it as part of the COMP2300. The exam, as you saw in the mid-semester, the exam focuses on stuff which is not programming in assembly. You've got many assessment tasks that are related to programming assembly and showing us what you know that way. The exam is looking at different learning outcomes. So there won't be any coding questions in this exam either. I'm sorry if you're disappointed about that. I know we all love the little coding questions, but it's just really not what this course is about. So it's not the only thing that this course is about. So the exam looks at some of the other learning outcomes that aren't so clear from assignment work. I'll of course post about this exam stuff publicly in the lead up to it. So we asked this question on Monday: what even is a computer again? And we talked about a number of aspects of what a CPU is, how the components fit together, and particularly looking at a number of ways to replicate aspects of it, which gave rise to this idea of multiprocessing, or having multiple components in a CPU running multiple programs at once, or doing multiple jobs at the same time. So that was the Flynn's taxonomy idea. The other idea we talked about was the CPU design idea of CPUs where you have a separate program memory and a separate data memory, or the situation we have on our CPUs where there is a unified memory architecture that is connected to one single address bus and one single data bus, which lets us access program memory and data at the same time, all through the same interface, which is really handy for programs that would like to update themselves, or programs that would like to write programs. So that's the von Neumann architecture, which we always use, or we tend to use. When you dig deep into the microarchitecture of a system, you tend to find that there are different memories within a CPU for temporary storage of stuff called cache. And sometimes there is instruction cache and data cache. So internally the CPU has this, maybe a different architecture than what you might expect from the external situation. But that's the internal situation on a modern CPU is like that. The very simple CPU which we looked at was on my little board here, and this was the 6502 CPU coming in that 40-pin package there. And we talked a bit about how it had these, lost my pen now, it has what we would expect, which is an address bus. There's the address bus, and it has the address bus continues up there, and it has a data bus. It's an 8-bit data bus, 16-bit address bus. That's ground or positive or something. It has 2 interrupts. It has a reset interrupt. There's the 2 interrupts, IRQ and NMI. And it has some inputs for a clock so that you can get it to tick along. It's got some no connections, and it's simple enough that you can really understand how this thing works without too much effort, with the knowledge that you have already about what a CPU is supposed to do. And the cool thing about this example is that, well, on this little computer you can see very clearly that there's RAM, there's ROM. The ROM is the program memory, which is non-volatile, just like on your microbit, but in the olden days, Flash wasn't invented yet, so this computer itself can't update its own ROM, whereas your microbit can update its Flash memory itself. This thing is called the Peripheral Interface Adapter. We're going to talk a bit about that today. It'll become interesting. And then we've got a couple of other chips, and these chips here are actually logic gates in a chip. And I'll just see what number that one is. 74LS00B1. 74LS00B1. That one would be a quad 2-input NAND gate, classic chip. I should know that one by heart because it's such a classic. I want the data sheet. I don't want to have to know what things are. Give me the data sheet. Download. I just want to see the PDF. Okay. Here's a picture of what this chip looks like. It's literally 4 NAND gates, logic gates, inside that chip, and it's got a ground connection and a voltage connection. This is a really typical arrangement for a small logic chip. You don't see these very often on electronics anymore, because like this chip, it looks small, but it's huge. Like if you put that inside an iPhone, you wouldn't be able to fit anything else in there. So things aren't made with chips like that anymore. But in the olden days, we did use these kind of chips to make entire CPUs. You can make whole CPUs out of what these are called discrete logic chips, or separate logic chips, or you can use them as what we might call the glue logic of a computer. And the point of having glue logic is that you might want to make some kind of logical calculations with the CPU outputs. And the most typical thing you do is take the address outputs and use some NAND gates to decode what address is happening and turn on different chips. So if we go back to my, I wonder if I've got a picture of this computer's layout. Oh, there it is. So, oops. There's our RAM, and the RAM is going to start at address 0000. There's a 16-bit addresses here. 0000, and it's going to go up to address 7FFF. That's 32K of RAM. You might notice that there's sort of a significant digit here, the top digit. In these olden computers, people thought of memory as working in pages, and we often do think of that in different arrangements. And each page would be that much memory, which is 16 times 256. What's that? 4K, I think. Oh yeah, that's a page on our microbits memory as well. So we got, someone can't see where I'm writing. Oh, whoops. Thank you. Turn off my little camera. I'll write it again. Oh. I'll write it again in red. This is our RAM. This is our ROM. The RAM starts at 0000, and it goes all the way up. I'm going to draw it on the thing. It goes all the way up to 7FFF. And then the ROM, like, it's not exactly in any particular place, but it needs to be wired in to certain values. So, whoops, I really didn't want to do that. I'm trying to find an address map of the Apple One now. I've lost it. Lost my train of thought. Apple One memory map. Oh, that's the picture I want. There we go. We got our, this is the actual RAM on this system, the replica one. I'll go to the page for it. This very computer that I have here. So, RAM, user RAM. Oh, it says it can go up to have some scratch memory. I don't know what's going on there, but everything above in the second half of this RAM is going to be the stuff in either ROM or peripherals. So the ROM is everything in the F area. Then there's a program in the E area called BASIC, which is also stored in ROM. Then we've got the PIA I/O area in the Ds. The Cs, which was traditionally with the Apple One, would connect to a cassette interface, like literally an audio tape, because that was the easiest and best way for average people to store data from a computer. You would connect a tape to an interface, a cassette tape, and the bits would be encoded as an audio signal on the tape. And that meant that you could store a program and load it back on your computer. And little cassette tape machines were fairly inexpensive. So they were quite easy to use, and people were using those into the 80s. At that time, like even things we think of as floppy disks as being really old, boring technology, in the 70s and 80s, they were quite expensive to get a floppy drive. So cassette drives on the first era of microcomputers were really ubiquitous. The Bs aren't used for anything, and then there's maybe some firmware used in the 9s and the As. I'm not sure how much of that is actually on my ROM in my machine. I haven't explored it that much, but that was the basic thing, is that we need this chip to respond to any address that starts with an E and any address that starts with an F. And then we need this chip to respond or to get a signal when we get things that start with a D. So when we go back to our chip, that means that we can decode what letter or what number is in that top 4 bits by looking at the values of these pins, A12, 13, 14, 15, and doing some logic gates to work it out, right? So I could, work out that the pattern for D should be what? I've forgotten right now. What's D? A is 10, B is 11, C is 12, D is 13. So it's going to have a 1, it's going to have an 8, it's going to have a 12, and it's going to have a 0. So that number is going to be D. So you could work out with some not NAND gates, like a way to get a 1 back when it has exactly these bits set on those top addresses. And when that's the case, you could then send a signal to the PIA to say, you're on, select you should be listening to messages right now. And then the other addresses or other lines are used to control the PIA. And when it gets the signal for this one, it turns off or disconnects the RAM, so it's not listening anymore. So you can do that with those logic gates that come on those little chips. And cleverly, the designer of this particular replica figured it out so you only need 2. 1, 2, 7/4 series logic. This other one's another one. It's probably not NAND gates, I don't know what it is, but it's another 4-pack of basic logic gates for doing this kind of address decoding. So let's have a look at how this thing actually does some stuff, because you might not know. If I got my system here, there we go. So when I press reset, you can see I get a character. I get a little slash. I'm just going to change my screen around a little bit. You can just imagine that you're still looking at the system there on the screen. We get a slash, and you might be thinking, oh, this is great. It's running some kind of operating system. And you might go like, CD home or something, but it doesn't know that doesn't seem to make much sense. Make the help. It doesn't respond to commands because this is a very simple computer, and it in fact doesn't have an operating system. It does have a program which runs whenever you turn it on, and the program that it runs is called the WOS monitor, or WOSMon, which is named after Steve Wozniak, who designed this computer originally in the 70s. And the way the WOSMon works is that it lets you look at memory, it lets you change memory, and it lets you start programs. So let's have a look at some memory. 300 has that's a byte, and it's got the value 55. Get some more memory. 300.32F. It's going to give me a string of memory. And you can see it's just full of uninitialized values. 555555, 55555. Why is it full of uninitialized values? Because I've turned it off and turned it back on again. If I want to set some memory, that's not too hard. I can just say 300 FFEED, and then I can go 300.32F and see my FFEED. You might hope that this is a terminal where you can go back, but in fact, you can't. It doesn't work like that. This is not a fully interactive terminal that has a buffer where you can see the previous command. We're sending serial characters over a serial port to this computer, and the CPU is literally processing those characters one at a time and then throwing them away. So it's reading, we're sending 0300 or 300 and then the enter key, return key, and then the computer does what it can do knowing that it's just received 3 numbers. So it doesn't have any way of storing, or in this program it doesn't store previous commands, it doesn't let you go back. The serial interface is very limited. It's printing things out to me, I'm sending characters back. We can enter an actual program here. So I've got one written down, and this may not look like a lot. I've got it here in my second window. Here it is. You know, it's that old classic A9 O AA 20 EF FF E8 8A 4C23. I know that you know what that is, right? Let's enter it in and see what it does. A9 O AA 20 EF FF E8 8A. By the way, I have to do capital letters only. It can't receive lowercase letters. 4C23. It literally doesn't have enough pins connected to the serial port to receive an ASCII character of a lowercase format. That's my program. I think it should be right. Okay, so whenever you press enter, it tells you what was previously in the first byte of that memory, which is a bit of a weird thing to do. I don't know why that was a good idea, but I guess it was. So there's my program written in memory, A900 AA 20 EF FF E8 8A 4CO203. Great program, let's run it. So we're going to just say to WASMON, just run the program starting at memory address 300. And there it goes, it's running this little program. And what does this little program do? It prints out a lot of characters. And the only way to stop it is to reset the computer. Fun. Now I've got on my screen a bit of a translation of what this program does. So that you can see, it's only a short program. The way that 6502 assembly code works, or the 6502 instructions work, is that they can either be 1 byte, 2 bytes, or 3 bytes. So there's instructions of different lengths depending on what kind of instruction it is. And it's quite an interesting instruction set. It's got some interesting addressing modes. It has a lot of instructions that read things directly from memory and use them as the basis for a calculation. So in that way, it's quite different than what you might be used to in ARM, because ARM is strictly load store. If you want something from memory, you've got to load it into a register and then load something else into a different register and do something with those 2 values and move on. But in 6502, it's not load store. So we can actually enter this into, I'll just give this a go, enter it in a disassembler over here, get that program. So it tells me what's going on. You can disassemble this with this little program. It's very easy to assemble and disassemble 6502 because there's many fewer encodings for different instructions. Anyway, we'll look at it on my screen here. I'll just explain what it does. The first instruction, A900, it loads a number, 0, into the accumulator. So LDA loads something into the accumulator. And in this case, it's loading an immediate, so it's the immediate version of LDA. There's some other versions of LDA that load from memory or load in memory with different addresses, different addressing schemes. This a 1 byte instruction, TAX, transfer from the accumulator to the index X register. 1 byte. Next one, 20 EFFF. This one is like BL, so it's jump subroutine. Similar to branch with link. And the subroutine is going to be found at memory address FFEF. And you can see that it's put it in here in little endian format, FFEF. And FFEF is actually a subroutine in the WAS monitor. So that's a subroutine which knows how to print something onto the display, or onto the output of the computer. So we'll look at that code in a minute. Then what do? Increment X E8, it's a 1-byte instruction which just adds 1 to whatever is in register X. 8A is transfer X to accumulator, easy enough. Then we jump back to 0302. So this is a very, very simple program. All it does is starts with values, 1-byte values starting at 0, and prints them out onto the display, which interprets them as an ASCII value. And it has no limitations, it just loops itself around, keeps running forever. It doesn't do any conditional branching or anything. So you might wonder, are we following me so far, or is this really boring and weird? Just see if there's any pertinent questions. There was a question a little while ago. Surely one doesn't need that big a chip for 4 logic gates. I'm sure they don't. I just don't know. If you wanted logic gates on a modern circuit, it would come in a tiny little package that is surface mounted on the circuit board, like the little very microscopic chips on the back of the microbit, which are also tiny. But I just don't think that the microbit has that many. It doesn't have anything like 7/4 series logic. It's got a couple of single transistors. And you can see they've got 3 legs. But then I just don't think you don't need to do the glue logic as much with modern design. It's my understanding anyway. I'm not an electronics engineer. I just think it's the 7/4 series logic is a bit of a past design thing, but they're still cool. Actually, by the by, you can make a synthesizer with 7/4 series logic quite easily. If you get you can get one that has 6 inverters, just NOT gates, and you can use that with a little RC circuit, a resistor capacitor circuit, to make an oscillator in just a few components and make something wild. So anyway, this is way off topic. We're not talking about synthesizers today. The question was, the transistors on the microbit are microscopic. They are inside the packages, but there are some on the board. I don't have a microscope with me. I mean, you can see microscopic things with your eyes. Microbit v2. tech.microbit.org. I really want a high res, zoomed in photo at the back of a microbit. These are all diagrams, aren't they? Like inside one of the chips, they're microscopic. But there are also some, I mean, they might be, I'm just guessing they're transistors. They could also be like a voltage converter or something. I wouldn't know. I haven't looked in detail at the thing. I'm trying to find a good picture of a microbit. How will I ever find one? These things. So inside there, lots of transistors. Many transistors. Then these little guys, what are they? They're things with 3 legs. They're small, but they've got 2 legs there and 1 leg there. And that's just, you know, I'm not an electronics engineer, but when I see a 3-legged part in electronics, I tend to think it's a transistor. Electronics, transistor. Like when I was a kid, you'd still see these ones. In fact, I think there's one on the the replica one I've got here, that's one single transistor, which is quite a big part by comparison. Almost it's like 1/2 centimeter across with 3 little legs. Transistors have that kind of 3-legged thing, base, what was the other part? Emitter, collector, that's the parts. You're testing me on electronics now, folks, if you're going to ask questions about this. Packages, that's 2 transistors in one. Yeah, I don't know, maybe there's something else. You'd have to get a microscope out to work out what those little things actually are. They probably don't have it. They may have writing on them, but there's no way we're going to be able to see by ourselves. Some clever bunny can go away and find out what those things are and tell me later. But transistors are definitely, like, the actual silicon bit might be very small, but then like the manufacturer puts it in a plastic package that lets you deal with it more easily. So if you want to solder one of these onto a board, it's going to be very difficult if you're hand soldering it. Those ones are placed by machine on little solder pads, which have already had a little dab of solder put on them by a different machine. Then the whole thing just goes in an oven and the solder just melts. For my replica one thing, everything's hand soldered, right? And it's got sockets, so you can take things out and put them back in if they break. But I've gone on a very long digression here. Where was I? Oh yeah. Not that terminal, other terminal. Very long digression into this program in assembly on the replica 1. So if you had a replica 1 in 1977, what was your experience? Well, you would buy this thing, take it home. You'd have to already have quite an expensive keyboard which could connect to it, because it needs a keyboard that has an ASCII interface. It provides ASCII text. And you'd already have to have a screen which can accept ASCII text as well. So that was, or a terminal. That was a limitation on computers in the old days. And then you would be able to write programs and enter them in machine code in hex directly using the keyboard, which wouldn't be much fun. And a lot of people didn't want to do that, but they tended to use a program called BASIC. And you may never have heard of BASIC, but BASIC was, this is my, I don't know if someone will challenge this, BASIC was the Python of the 70s and 80s and early 90s. When you had a computer and you wanted to do some coding, you would just open BASIC and just start doing something. So it was intended to be, it's in the word BASIC, but intended to be sort of easy and accessible, a lot like Python, but was also very useful for a large range of people who used it for all different kinds of useful and amazing programs. So this computer has BASIC built into it. On the original Apple II, I think you had to buy a tape that would have BASIC on it. And then you would have to spend 30 seconds playing back that tape into the computer to get it to load BASIC into RAM, because it didn't have enough ROM space. ROM space was very limited. So now I'm in BASIC. You can see I've got a little right-angled bracket there, which means I'm at the BASIC prompt. So now I can make a program. A funny thing about programming in these olden days was that because we had these terminals where you couldn't go back and you didn't have a whole screen full of information to edit, you could only edit one line at a time, you would tend to edit line numbers. And part of the reason for that is that then you can tell the computer, okay, I've messed up line 20, I want to go back and just change line 20. So here's my program. Hello world. Well, I want 20 to be something different, so I'm actually going to say 20 go to 10. List the program, I think. There's my program listing. 20 go to 10, and now I'll run this one. And what do you think is going to happen in this program? Print hello world, 20 go to 10. It's going to print hello world over and over and over again. This is a classic kind of first basic program, is making the computer print hello world over and over again. People wrote all kinds of fun programs in BASIC. It was really popular as a hobbyist or educational or exploratory thing to do. Create a program in BASIC. People might write like a little text-based game that would make a random number and you'd have to guess it or something, or you'd have a little adventure in a basic prompt entering things. Some systems would have like kind of system calls you could do from BASIC to draw on the screen. So you could make a program which would draw a graphical thing if they happen to have a graphical display, like on other microcomputers later, like Commodore 64 and Apple II. You could draw a nice display that would be programmed in BASIC. What else was I going to say about BASIC? Oh yeah, the funny thing about this, which is it's just wild by today's standards, if you wanted to learn about BASIC and try out some programs, well, you couldn't just go and look on the internet, but you could buy a book. And there are books and magazines that would just be full of BASIC code on the pages, and you'd type the code in and make your program work that way. One more demo with the Apple II, with Apple I, I mean. Sometime later, when this replica was designed, people started playing with it, and a person who was playing with it was a researcher in Australia called Ken Wessons. And Ken Wessons wrote an assembler which is actually running on the Apple I. So the assembler inside the computer. It was 4K, so it's quite big and certainly wasn't included in those days, but it's a pretty cool little program, and it means that I can type in some 6502 assembly and make another program work. The question is, how come when I stop a program it prints the last character again a few times? Don't know. I think probably because when I press reset, like it jumps into the reset vector and starts running the startup procedure for the WAS monitor. And maybe that has some little a break for a few cycles, and in that break for a few cycles, I'm guessing here, so don't take this as golden information unless you have an oscilloscope and can find out. When you press the reset, maybe it breaks for a few cycles, but the clock is still going, right? The clock is constantly going up and down. The serial output is seeing the clock going up and down and is seeing a character W on the peripheral interface adapter's output and is saying, oh, I guess I write another W, I guess I write another W, I guess I write another W, until the CPU catches up and resets everything. So the PIA is still displaying a W, the clock is still moving, so therefore the system still wants to display that. I'm not sure if that would have happened on a real Apple I. Probably not. It might be an artifact of the serial interface for this one. All right, where was I? I want to start the assembler. I've got a few more demos to do today, and some microbit ones as well, so I want to keep moving. The assembler lives at FF00, I think. Is that how you do it? There we go. No, that's D. F000. F000R. Okay, Crusader 1.3 by Ken Wesson. Fun fact about Ken Wesson, ANU student. Finished his PhD at ANU in 1993 I think in mathematics. And then has had a career working in different things around Australia. I got in touch with him the other day because I realized he might be Australian and found out that he's one of us. So if you're interested, reach out to Ken. He's on LinkedIn. He says hi. Crusader, again, we're very limited by our interface. We can't just type things in and edit them later. We have to type line numbers. I've got some line numbers for a program here. This is the same kind of program, but we're going to do new, capital N for new. Okay. LDA, and I can't mess this up because if I do, package, back in a sec. Whoops, sorry about that. It's fun lecturing at home because when I get a package, I can go get it. Some research tools for a project that's happening. When we get to the exam period, I get to do some research. So I've got a label here, loop, and then jump subroutine again, FFEF. You know what that does now. It goes to the wasmons bit that prints a character. 2 CLC, that clears the carry bit. 3 ADC, you know about that one. We actually only have add with carry on the 6502. There's not a separate add that doesn't use the carry. It's always add with carry, and that's just going to add 1 to whatever is in the accumulator. Next one, CMP, just works the same as you would expect from ARM assembly. A bit of a weird literal format, but A is just the ASCII character A, you know that, and Z is the ASCII character Z, and then +1, the assembler is going to make that the character Z's code as a number and add 1 to it. So it's comparing with a regular number there. BNE, you know what that means. Back to loop. And then at the end of it, we, RTS, I've forgotten what it stands for, but return from subroutine. So that's like BXLR. Okay, I think I'm done. So I press escape, and now I can list my program. L lists my program that I've just written. That looks good. I could change a line if I wanted to, but I don't want to. I'll press A to assemble it. It did so, and it's saved it into memory at that location, 0300 030C. So now I can run it. Run $300. Similar kind of program. It just does the same thing, or the same thing as we were doing before. Whoops. R300, just printing the letters of the alphabet this time. Not going back and adjusting those things. So you've seen now a program that has more of this kind of while loop with BNE, with conditional branching working. But I wonder if you're interested in what FFEF does, because it shows something more about how hardware fits together on this system. And to learn about FFEF, we're going to have to look at this book, which is the Apple I operation manual that came with the Apple I computer. So here is the 8K bytes, 4K supplied. If you wanted to run BASIC, by the way, you'd have to buy another 4K of RAM, because the 4K you come with, well, BASIC would take up 4K, so you would need another bunch of RAM just to deal with BASIC. So this is a short manual, 15 pages, and that's the picture of the system actually. But the bit I want to show you is here. Here's the instructions of how to use it when you turn it on. You get the hex, the system monitor, that's the WAS monitor. And then you might want to know how the WAS monitor works, and that's great because here it is. This is the actual program that runs when you turn on the 6502, the Apple I. And Steve Wozniak was a technical genius, and he wrote this whole program. This is literally 256 bytes of memory. So that's his program for the system monitor. Very, very tight. At the top of memory, FFFE, FFFC, FFA, these are the interrupt vectors. So when the computer resets, it looks in address FFFC, finds a memory address, and then starts executing a program from that location. So the first thing that happens when you start the WAS monitor is it goes to OOFF, which we can find, FFOO, and ends up at that, which is labeled reset. So clears decimal arithmetic mode, clear something else, start doing some things. But what about FFEF? Here is FFEF. So it's the echo function, and what that does is takes a 8-bit number in the accumulator and prints it on the screen. So if it's an ASCII character, they're all 256 different bytes can be interpreted as an ASCII character, so it puts it on the screen. What does it do? Well, it does this BIT, which is going to be doing a test on DSP. It's a bit of a complicated instruction because it's doing multiple things at once, and you can interpret it any way you want, binary test. But basically, we're looking for one thing it does is copy the top bit, the 8th bit of whatever it's pointing to in memory into the carry, into the negative bit, the negative flag. So then we can use the BMI instruction to decide whether to go back to echo and wait or to continue. So what is this DSP? Well, that stands for display, and it's just a kind of a dot set, a internal variable pointing to this location in memory, D012. Remember at the start of the lecture I said that the PIA was connected to all of the Ds. So in fact the PIA is only connected to 4 Ds. You've got D010, D011, D012, and D013. So there's only 4 addresses that it's connected to. And when they're connected, when I say connected to, I mean we're using those logical connections to maybe just work out whether we're in the Ds, and if we are, we send a signal to this pin. This is the peripheral interface adapter, the chip select 2 pin, which is going to turn it on, and then A0, A1, and A4 are also connected. A4 is connected to turn it on as well. That's one of the other chip select pins. There are 3 chip select pins on the 6821 for some reason. And then, so we're actually only using A0 and A1, which are the first 2, the lower 2 bits of this nibble, which are telling the PIA what to do. And the PIA is actually, it's a fairly simple device. It's got an input, which we can't see here, the data bus, D0 to D7. That's all kind of obvious there, all compressed. It's got 2 ports, which are another 8-bit bus, port A and port B. Now port A can either be input or output. And basically what you're telling the PIA to do is to either read things from the data bus or send things out on the data bus. So you've got an RW port for that. And the keyboard is going to be on PA, port A, and the display, or ASCII to display with some other circuitry, is going to be on PB. So when we're reading, what we're doing here is waiting for bit 7 of the display port, PB7, to be clear, because there's some way that they've worked out to use that pin to detect the end of the message to the display for a single byte. I don't quite know how that works. I'd have to do more digging, but they're using this single pin on PB just to say the display is now ready for another character. Then when we actually want to send a character to the display, we're saying store whatever's in the accumulator to the display, and that will set these bits the correct way, and they will get sent to the display and print out, and then return from subroutine. So, no one's asking any questions, so I suppose everyone who's listening understands everything. I'm going to do 2 more sort of speculative little demos now. We'll say goodbye to the replica one. We've had some fun with it. I always enjoy going a bit further with 6502. I've done this demo 3 times now. The first time I think I just ran the program, then last time I did it I ran the program in hex and then basic, and now I'm using the assembler. So every time we go back on COMP2300 we can do a few extra things. But a few things I want to talk about. I guess there have been a few questions on the forum about like how programs might work. And I want to start from my my supervisor call program last week. How programs might work if you had an OS. And I'm talking to Adnan here. So Adnan, you're the question asker extraordinaire with relation to questions that really stump me. And the question was, like, how does your microbit make sure that if it runs a program, that program can't then get more privileges, for instance? So we haven't really talked about how programs get privileges and what those privileges prevent them from doing. But we can, a little bit. We can. So, what we need to do is look at this program and recall that we've got our main function that's starting. This function, now that you've seen how things work on the 6502, you might actually go into the startup script and see that our startup script also starts at reset handler. It starts in the reset vector, exactly the same way. And then the first thing our reset vector does is copy our flash from RAM so that it's read-write, and then it calls our main function. So we could imagine that the main function is actually the start of our operating system. So what the main function will do is decide to set some things up. And one of the things it might set up would be I'm just getting my ARM v7 manual out while I'm here. It might set up the privileges for other code. Oh no. Oh, references and links, that's the one. ARM architecture reference manual. And you might notice, if you haven't noticed, when we run a program, there's actually a lot of registers that we don't use and we haven't talked about in this course. Uh-oh. Oh, it's because I haven't got a microbit plugged in. Sorry, unplugged, bye-bye. Apple One, hello microbit. Got my microbit. I was having a terrible time last night trying to debug some code. It just wasn't working. Turned out I was in the emulator. Oh dear. Yes, so we've really only talked about registers R0 through R15 up to PC and the XPSR, which is all good. But then there's these other ones, D0, D1, D15, FPSR, MSP, PryMask, base pry, fault mask, control, and then the S0s, and all the way up to there. I'm not going to say that I know what all of these do, because CPUs are complicated, and I'm learning with you folks over many years. Every year we get further into the things that we can teach in COMP2300. But I do know that there's a useful register here called control. And control is actually a 3-bit register, and it's only got three things: FPCA, SPCell, and NPriv. So we have to look in the manual to see what those things are. The special purpose control register. So the special purpose control register is a 2-bit or 3-bit register. In our case, it's 3, defined as follows. NPriv defines the execution privilege in thread mode. What is thread mode? What is thread mode? You remember that we had 2 modes of operation in our Cortex M4. We talked about this in the operating systems week. One is thread mode and one is handler mode. So normal code runs in thread mode, and if you're in an exception handler, in interrupt handler, you're running in handler mode. So this is one of the reasons why it's bad to always have your whole program coded inside an interrupt handler because it will always be running in handler mode. Normal code runs in thread mode, which means it has to be not in a handler. And the CPU knows whether it's in a handler, right? The interrupt is fired, it knows it's in an interrupt handler, and until you get to the end of the interrupt handler and you send that special value, BXLR with the special value, you're still in the interrupt handler, so you're still in handler mode, which is always privileged. But npriv defines the execution privilege in the normal thread mode. And this is great. I can change this bit to say thread mode has unprivileged access. All I need to do is change it to a 1. We've got two other things here, which we'll just briefly look at. SP cell define the stack to be used. That's interesting. So we've actually got 2 stacks on the microbit. You thought we had 1, but we've got 2. You can have, there's only one SP, but SP can point to a different value. And there's only one memory space, but you can have a different value set up for SP. So your operating system could run on the main stack, and your program could be running on the process stack. And so you don't have to delete your main stack when you're running your operating system code. And then the FPCA bit is related to floating point extensions, which we don't cover in this course, so I'm not going to worry about that. So a reset clears the control register to 0, and software can use the MRS instruction to read the register and the MSR instruction to write to the register. Well, this is great. So the first thing my program might do is use, what was it, MSR, I believe. And I think we want to do, I have to look now in my MSR instruction details. I should know this by heart, but I don't, because I never use the MSR for anything, only for this demo. MSR, special purpose register. Okay, so all you do is say, that's not very much help either. Move to special register from ARM register. Yeah. What does it mean by unprivileged access? I'll tell you in a minute. Just keep that question in your mind. What does it mean by unprivileged access? Well, just remember what I did last night. Somehow it's disappeared from my mind what it's supposed to look like. Oh yeah. Bit 0 is npriv, yeah, gotcha. Okay. I was doing this little experiment last night. Move R0, 1. So that's npriv is bit 0 of control. MSR control. Move my terminal down a bit. And yeah, so I should be ready. I'm just going to put a few nops in here. Stop, build debug. Okay, so we're going to set our control register to set npriv to 1. And that worked. We're now, folks, in unprivileged mode. So it's a bit kinky, but you can imagine we've just put the handcuffs on our Cortex-M4. The Cortex-M4 is now not allowed to do certain things. And one of the certain things that it's not allowed to do is turn itself back into privileged mode. So let's see, can we do it? Can we get out of unprivileged mode? Let's just have a little look. So we're turning ourselves, so if we set the control register to 1, bit 1 to 1, we are putting ourselves into unprivileged thread mode, we're in thread mode right now because we're not in an exception handler. We're an interrupt handler. Now I'm going to try to change it back to 0 to let myself be privileged again. I want privileges, I want privileges. And the processor said, no, it didn't change. Folks, we're trapped. How do we get out? How do we get out of unprivileged mode? Well, what we are allowed to do, as you remember, we've got our supervisor call instruction, which lets us go into handler mode, into a interrupt handler. And this was what we were looking at last week. We looked at how we could get the argument out of the supervisor call by looking in the stack, finding our return value, and then just going back a bit and loading up that value. But what we could also do while in handler mode is give ourselves our privileges back. So the operating system might choose to give return privileges to our software. So we're now in unprivileged mode while in thread mode. We can't change it here, but we do a supervisor call and the operating system now, which is running in handler mode in this interrupt handler. Should be able to do this, I hope so, because I haven't tried it. Phew, it can. So the operating system has given us back the privileges and returning. Now, someone's asked a really good question. What do I mean? What do you mean by unprivileged access? So on Cortex M4, there are 2 modes of execution. Thread mode, normal program. Handler mode. Handler mode is inside an interrupt handler. That is time between interrupt starts and BXLR to something, N. 2 modes of execution. Then we've got 2 privilege levels, privileged and unprivileged. Now, you've just seen that when I'm in unprivileged mode, there are certain things that you cannot do. And one of the important things is you cannot change yourself back into privileged mode if you're in thread mode. Privileged mode, you can control, access all memory and change all processor settings. I'll put it that way. E.g., change back to so if we had this concept of unprivileged mode and privileged mode, and we had a program which we wanted to run in unprivileged mode, it wouldn't be much point if that program could just change itself back to privileged mode quickly. So how might we change ourselves into, change ourselves into unprivileged mode and run a program? Well, what we could do is, now I've set the SVC handler to this is going to set thread mode to be unprivileged. And then we're actually going to run a program. So run a program, and I'm going to do this in a really bad way. Not a bad way, I'm doing it the way I should do it, but I'm not doing everything that I could do. I'll make a program down here. Function. Naughty program. So my naughty program needs to have its privileges restricted because it's in the naughty corner. And all I'm going to do to get this to run my naughty program is change the return address in the stack. So if you remember, when I run, I have to look in the manual again. When I am inside an exception or an interrupt, exceptions being interrupts, a lot of things end up on the stack. Here's my basic stack on exception entry. All of these are R0, R1, R2, R3 have been stored on the stack, R12 is stored on the stack, LR is stored on the stack, and the return address of where I was before the exception started is stored on the stack, and the XPSR. So if I'm in a stack and I want to go back to a different program, a different part of my program, all I have to do is change the return address. I could change this other stuff as well to make things work, but I don't care about things working right now. I just want to end up in a different part of my program. So I'm going to letter R0 equals naughty program. That's the address of my program. Remember, if you want to run a program, you're just BLing to that address, just like on the Apple I. And then I'm going to store it on the stack at 0x18, store in the return address. Stop that. And my naughty program, of course, is going to try to get itself out of unprivileged mode. And we'll find out that it's not allowed to. Okay. Into the supervisor call, some stuff we don't need to worry about right now, which we did last week. Set the thread mode to be unprivileged. Yep, npriv is 1. Now I'm going to make sure that I return to my naughty program when I bxlr, and I will bxlr and I end up inside the naughty program. And now the naughty program is going to try to set its privileges to privileged. And it can't, because it's stuck there. It's not allowed to leave. So I've got myself a program which cannot make itself privileged. What can you do with privileges is a good question. The answer to that is that you can control the memory protection unit. Where is the MPU? Exception model, floating point, memory model. I forgot where the MPU stuff was. Well, I'll search. I'll go into the, what about the contents page? That'll be good. Memory protection unit. Protected memory system architecture. So, what's the point of unprivileged and privileged access? There's two things. You can't control certain aspects of the CPU. And the other thing is that the CPU has a feature called the memory protection unit, which means that it can block an unprivileged program from accessing or changing or executing certain bits of memory. So what we can do is turn on the MPU, which would mean that then our little program couldn't actually change any memory that it's not supposed to. Now, I'm only a little bit confused about how to get this to work, but I'll give it a little crack. I'll just set up a dot set, I don't know, address MPU, oh that one, I used it in a different program, E000ED94. On the microbit, all of the E's are the control space, memory mapped registers for controlling CPU features. So if you ever see an E, that's always a Cortex M4 thing. So I'm going to get my control register. I've set thread mode to be unprivileged. And the next thing I'm going to do is say, program, you're not allowed to run any code. Turn on the MPU. Naughty program can't read memory. This is not going to work very well because I don't know how to use the MPU properly. I'll probably do some research on it and figure it out for next week, but I'm possibly straining your patience with my demos today. And I'm going to get into R1, OB101. I need 101. It's got a 3-bit memory, a 3-bit register here, memory control register. The lowest bit is enable. There's this thing called Hufenminja, which I don't really understand why you would need that, but I'm not going to set that one. Then I need the privdef-enner, which enables a default memory map, which means that my privileged code is actually allowed to read memory. If I don't set that one, the privileged code isn't allowed to read any memory by default, which is bad, causes my program to crash. I am not actually going to set up a memory map here. I'm just going to run it to see what happens. But you should see that as soon as I go out of my handler, my program crashes because the CPU is trying to, it exits handler mode first as soon as we escape from the interrupt handler, and then it tries to put those registers back from memory, and it can't. So I will enable unprivileged mode, npriv1. I'm going to turn on the MPU. It should make a cool noise when you turn it on. And then I'm going to go into my program. Oh, it worked. Well, that's weird. Didn't expect that to happen. Wonder what I did last night that made it not work. While I'm in this program, can I load some memory? I've probably gotten this wrong. 1, 2, 3, 1, 2, 3, 4. Oh. Oh, I didn't actually save my MPU value. That'd be the reason. Store R1 R0. I didn't actually turn on the MPU. Yeah, it will definitely crash this time. Turning on the memory protection unit. Memory is protected, but it's too protected right now. And my program actually crashes, ends up in the default handler. That was bad. So I need to do some more work and set up a memory map. I'm not going to do that today, though. I just want to point out a few things about exceptions. To return from an exception, we normally have this number in our return value. Let's get back into an exception. You can see it here. LR is FFFF9. That's the special return from exception number. But there's other options for it. You can go return to handler mode. If I put in FFFF1 with the same stack, I can return in thread mode, and I can return in thread mode with the other stack, the process stack. And then with our FP extension, which I think we have, there's even more options. So I might try this one. I'll see if it works. I don't know what happens if I do that. FFFF1. So I'm actually going to make my naughty program part of the operating system right now. It's like giving it sudo, because I'm saying please run this program inside handler mode. I don't even know if it's going to work. Letter R LR OX FFFF FFF1, wasn't it? I think so. We'll see what happens. Oops, cancel that. Now I've got FF1. No, it still goes into handler mode. There you go. I'll have to learn about how to change those values there. But it's something that you're going to learn about in Lab 12. COMP2300, labs. Because Lab 12 is about making your own operating system. And you get to do this next week. Once you're done with the assignment, you can do this, start getting inside exceptions and changing stacks and switching between fake programs. And if you want to, you can implement these privileged, unprivileged stuff and see if you can get it to work better than I could in this demo today. Folks, that's all I've got for today. You've actually made it. We're at the end of the content for COMP2300. Would you believe it? The lecture content. Next week is only revision after you get your assignments done, and then we're entirely heading towards the exam. And it's pretty exciting. I'm pretty proud of how everyone's gone this semester and how far we've managed to come with the microbits. So I'm really looking forward to seeing all of the wonderful things that you do with your digital pets. And with that, I'll connect to my thing. With that, folks, I will see you next week. Catch you on Monday. Good luck with your assignments over the weekend and everything else you're doing at the moment. See you later.